Hello everyone, I am Tenu Hasini, my supervisor Dr. Mangalagama Devasurendra. Today we are here to discuss about numerical study of thermodiffusion effect in boundary layer flow of nanofluid over nonlinear stretching sheet with slip and variable thickness under magnetic field. These are the outline of our research. First, we look at nanofluid. Nanofluid introduced by Choi and Esma in 1995. Nanofluid is the mixture of nanoparticle and base fluid. Base fluid like water, ethylene, glycol, and oil have low thermal conductivity. In contrast, nanoparticle like metals and their oxide have high thermal conductivity. Nanofluid increase the thermal conductivity of base fluid. Therefore, it has a wide range of real-world application. Some of them are automotive industry, solar energy, medicine drug delivery, heating and cooling system. Thermodiffusion effect, also known as Soret effect, is the tendency of convection-free mixture to separate under temperature gradient. Thermodiffusion effect was initially discovered by in Ludwig by Soret in 19th century. It has a various applications such as separation of polymeters and crystal growth process. Now let's look at formulation of our research. Take a study two-dimensional incompressible laminar flow of nanofluid over nonlinear stretching sheet. Here, silhouette located at the origin, x-axis taken along the sheet direction, y-axis perpendicular to it, u and v are the velocity component in the xy direction. We make some assumption. Pressure gradient and external forces are neglected. Fluid base and nanoparticle both are thermal equilibrium. Thermophysical properties of nanofluid have constant value at the boundary. Because of the third assumption, heat transfer and mass transfer happened. Boundary layer equation consists of continuity equation, momentum equation, energy equation, solute equation, and nanoparticle equation. Continuity equation describes the conservation of mass. Momentum equation describes the momentum of nanofluid. Energy equation describes the conservation of energy. Solute equation describes the conservation of solutal concentration, and nanoparticle equation describe the motion of nanoparticle within the nanofluid. This boundary condition will help to solve the above the five equation. These five field equation are partial differential equation. We define the similarity transformation. Similarity transformation will help to partial differential equation convert into ordinary differential equation. We apply the similarity transformation in the partial differential equation system. Then we get ordinary differential equation of these. And same way we get transform boundary condition. It will help to solve the transform governing ordinary differential equations. These physical variables related to our research. Now we at the magnetic field in our system. When conducting field moves within a magnetic field, eddy currents induced. The interaction between eddy currents and secondary magnetic field generate Lorentz force. Lorentz force opposes the nanofluid motion. Therefore, momentum equation reduced like this. So only this governing ordinary differential equation change, but boundary condition will not change. Now we assume our system has velocity slip. Therefore, near the flow near the velocity is not equal seat velocity because velocity slip is the relative movement between fluid and the solid surface. Here we consider second order velocity slip. Therefore, transform boundary condition also change like this. Now we make our stretching sheet contains variable thickness. How do we make our stretching sheet contains variable thickness? Change the thickness of sheet by tapering it. That is, one edge of the sheet is thicker and another edge is thinner. Variable thickness of stretching sheet refers a specific scenario in fluid dynamics. It was used in engineering application more frequently than flat surface. Because of the variable thickness, stretching sheet velocity change like this and previous boundary condition this. Now our boundary condition also changed due to variable thickness. Now our sheet is not flat. Sheet thickness defined this way. Previous similarity transformation also change x plus b in place of x. Our ordinary differential equation not change but transform boundary condition change because of the thickness. Previous model theta equal alpha but here theta equal wall thickness parameter. To make it easier, we define these variable. It will help to theta equal alpha to eta equal 0. That is, these variable change the transform boundary condition places. Therefore, our transform governing equation also change like these. These are high order nonlinear ordinary differential equation. So we can't solve directly. We need to choose proper numerical algorithm. Here we take optimal homotopy analysis method. Optimal homotopy analysis method is the most powerful mathematical tool for solving nonlinear problems. It is the combination of homotopy analysis method and optimizing the convergence control parameter by minimizing the square residual error. First, we define the nonlinear operator. Taken from our original problem. These OHM have great freedom to choose auxiliary linear operator and initial guess. Therefore, we take these are the linear operator and initial guess in our system. If we checking these, it is definitely satisfy our boundary condition in the fresh model. Now let's see the results of our research. Table 1 shows the comparison of the previous published results and our present work. Here we observed our results are excellent agreement. Therefore, be confident our results are accurate. In table 2 shows the different value of wall thickness parameter, magnetic parameter, first order velocity parameter, and second order velocity slip parameter. Then observe the physical quantities of interest. Here observe the results on below the table. Increase the wall thickness parameter, all the physical quantities of interest increase except local Nusselt number. Increase the magnetic parameter, skin friction coefficient and local Nusselt number increase. And increase the first and second order velocity parameter, second order slip parameter, only local Nusselt number increase. Now let's see the graphical results of our research. Figure A and B show the physical parameter impact on velocity profile and temperature profile. Here, red color curves denote the fixed value of magnetic parameter, first and second velocity slip parameter, and increase the magnetic first and second order velocity slip parameters denotes blue, green, pink color curves respectively, and thin and dashed line respect the different values of wall thickness parameter. Here we, according to our results, increase the wall thickness parameter, both profiles are decreased. Increase the magnetic parameter, first and second order velocity parameter, velocity profile decrease but temperature profile increase. In same way, we checking on solutal concentration and nanoparticle concentration. Here we observe the results has similar behavior previous temperature profile, but values are different. Now we move to the conclusion of our research. Finally, we investigated the impact of physical parameter on all the profiles of nanofluid by adding variable thickness in the stretching sheet. Partial differential equation convert into ordinary differential equation using similarity transformation. Now our system has magnetic field and velocity slip and variable thickness. Therefore, our system is the more complex system. But in the table 1, we are checking the previous results and our present work, we get an excellent observation. Therefore, we are successfully solved this system using optimal homotopy analysis method. And physical quantities of interest such as skin friction coefficient, local Nusselt number, local Chairwood number, and local nanofluid Chairwood number strongly affected by wall thickness parameter and these are the references we are using here. Thank you for all giving me this opportunity and participating this event. Make a memorable occasion. Thank you.